Constitutional isomers are very important in the sense that you have to understand that you can have many compounds with the same molecular formula. Okay, so you can have different functional groups, different structures, whatever it is, and then they are called constitutional isomers. Okay, so let's start. And so that is the definition also of constitutional isomers, is the compounds that have the same molecular formula but a different structure. Okay, so for example, C4H10 has two isomers. Hopefully now you're feeling a little bit better about nomenclature. So butane to methylpropane, you can draw the structures out and you will see that they actually have the same molecular formula. So butane would be this and 2-methylpropane would be this. Okay, and so those are constitutional isomers. So the way I always think about constitutional isomers is about like Lego blocks. And if you have Lego blocks, red, blue, yellow, whatever it is, you have all these different number of carbons and hydrogens and oxygens or nitrogens, whatever it is. And if each of you in a class of 20, say, get 10 Lego blocks, not all of you are going to come up with the same kind of design, okay, from it. So that is how I view constitutional isomers. Now, can you predict how many isomers you will get from a structure? Definitely not. So here are some examples like C4H10. Of course, that'll have only two because there's only so much you can do if you have less pieces. But then as the number of carbons increase, look at all of these. Look at how many isomers you can have. And I really sympathize with the person who actually did the C40 isomers, okay, how they wrote so many. I don't think they have been able to. There is no formula for this, okay. There is no formula to tell you how many isomers you will have, so don't even go there. It's just a matter of writing as many as possible for you. So the general information for writing out constitutional isomers is, first of all, you need to figure out whether you have an alkane, alkene, or an alkyne, which means you have saturation or unsaturation. So in which case, what you do is you look at the CnH2n formula, okay? What I do is I use CnH2n. CnH2n is easy to calculate. So if you have double the number of hydrogens, it means you have an alkene. An alkene means that I have a double bond. So if my formula has two more hydrogens, that means it is an alkane. If it has two less, it's an alkyne. So, take the middle ground. That way you can go either way, okay, when you need to, when you're calculating the number of hydrogens, okay? If you are given any halogen in there, Cl, Br, F, whatever it is, to write constitutional isomers, then you treat it just like a hydrogen, because hydrogens have single bond to carbon, so do chlorine and bromines or halogens. Okay, so that's kind of how it goes. Oxygen just fits in between the atoms. So oxygen you don't even count, okay, as an atom. You don't count it as hydrogen, you don't count it as anything, because oxygen will just fit in, okay, everywhere. You will see, okay, in all the structures I've drawn for you. If there is a nitrogen, then there's a slightly different way, okay, of doing the calculations, and I'm not going to worry too much about it. But as for nitrogens, you really only are dealing with amines then, okay, at that point, because nitrogen, the only functional group with nitrogen is amines or amides, and amides you also have to have an oxygen, okay, in there. So this is kind of a general thing, okay. There is so much more to this, all right. So we're just getting started. One of the most important things for you to do for constitutional isomer is keep it simple, okay? Keep it simple, keep it organized, all right? And you will see when I write my structures that I'm very organized about this. Otherwise, you will lose track of what you are moving, okay, what you're doing. So be systematic, number everything, and if you're not sure about it, name it also, okay? So write systematically. Number one, first of all, you move the carbons, okay, or the functional group. Either move one or the other thing. Don't move both things, okay, at the same time. So usually if I have a functional group in there, like a double bond, alkene, alkyne, or an alcohol, I will move the functional group first. Once I move the functional group to the point that I can't move it anymore, or I'm getting the same compound again, then I will start moving my carbon. Okay, so you take it a step at a time, all right? Don't try to overdo something. Number 4 is easy enough. Hopefully now you're comfortable with drawing structures out, so you know that if an OH is going up or down, It's the same thing because single bonds can rotate. Now, if you're dealing with cyclic compounds and you have something else, it's a different thing, okay? And you don't have to worry about that right now, okay? So at this point, just remember that whether something is going up and down in a straight chain, it's still the same thing, okay? So no worries about it. Number 5, try to write your isomers in a line structure, which means that don't draw all the hydrogens out, because once you draw the hydrogens out, you're really inviting trouble, okay? So you're inviting trouble for yourself, you're causing confusion, and you're wasting time, okay? So try to write in line structures as much as possible. You will see it'll work out. Number 6 is also a very good point here, is the fact that the first time you draw the structure out, okay, whatever molecular formula you're given, and you count your carbon and hydrogen for the first time, okay, and if you're getting the right number of carbons and hydrogens, then you can go on to the next structure, and provided you don't turn a straight chain into a ring or a straight chain into a double bond, you can trust me that you will have the same number of carbons and hydrogens. I will tell you which kind of compounds you can draw as constitutional isomers, okay? So this number 6 is a little bit dicey in some cases, but you will see what I mean by that, okay? And the last one is to help you with your confusion if you're drawing too many structures, which sometimes you have to, is that you number all your carbons, okay? Number the carbons, number where you're putting the substituent. Now, one of the questions that I usually get is, how do I know when I'm done, okay, writing all the constitutional isomers? So you gave me a formula, or you said that I gave you a formula, and you're writing structures, let's say it's a C6 6 carbon molecular formula. So when do I know I'm done? And the thing is that in some cases you don't, because as you saw in the previous slide, you can have many isomers, okay? So I tried to give you a focus that, okay, draw me 4 isomers, or draw me 6 isomers that are completely different, or give me 4 that have different functional groups, or give me 4 that have primary carbons, things like that, okay? So that should guide you a little bit as to how many structures you're supposed to write. Okay, so this is my guidance for you, and again, this is not absolute, it's a good start, okay? That is kind of how I start my constitutional isomers. So if you have alkanes, alkanes are just alkanes, that's it. You cannot do anything with alkanes. Like, you cannot take an alkane and try to write a ring structure with it. You can't, because you lose 2 hydrogens as soon as you go from an alkane to a cycloalkane. Alkane is CnH2n plus 2, cycloalkane is CnH2n, okay? So you lose 2 hydrogens. Alkenes and cycloalkanes, on the other hand, they will work out. That's not a problem, okay? Alkynes, if you're drawing an alkyne, feel comfortable to draw a cycloalkene also. It's totally fine. If you're drawing an alcohol, you can also draw an ether, okay? It's, again, not a problem. Those two are, I would say, like siblings, okay? So they're gonna go together. Aldehydes and ketones go together. So if you're able to draw an aldehyde, you should be able to draw a ketone. Carboxylic acids and esters go together, and all the amines go together, okay? So and again, this is not absolute, okay? This is not something written in stone. You can always intermingle into different functional groups depending on the formula that's given to you. So I am not going to go through all of these slides because it's a lot of it, okay, in there, but I want you to go over this yourself at some point and just take it slowly, one at a time. So I'm just going to go through it just so that you have this with you. Otherwise, I can't go through all of this, okay? It's way too much, and it's for you to actually just kind of go through and look how I've drawn the structures, okay? So this one, for example, C5H12, this is an alkane. So once you figure out that I have an alkane using the CnH2n plus 2 formula, so once you know it's an alkane, there's not much you can do. You start with a straight chain, you move 1 carbon, then you can move a 2nd carbon. That's it, So there's not much you can do. And so you'll have 1, 2, 3, 4 isomers, and that's it. You can't have any more isomers. So then here is for C5H10. C5H10 is CnH2n, which is an alkene. An alkene is also similar to cycloalkane. Okay, so the first thing that I did was that I have a straight chain, then I moved the double bond. What I have shown you over here is how you can flip a structure and it will look the same. Okay, so be careful, you know, when you're moving your double bond, don't keep moving so much that you think it's a new structure. These two are exactly the same. Okay, this has just been flipped like this, but you feel, oh, I'm moving the double bond from here to here, so it's a new structure. It's not. Okay, so if you flip it, you will still get the same structure. So this is a really good visual exercise also for us to recognize whether, you know, these two structures are constitutional isomers or different, or what is going on here. Okay. All right, so then here what I did is I moved a carbon also, and I moved the double bond. So in the first two, the double bond is terminal. You can see this is a terminal double bond, this is a terminal double bond going up, but these two structures are exactly the same. These two structures are not the same. Okay, so because in this case the double bond is terminal here and the double bond is internal. Okay, in this case, so these two are not the same. So which means I have 3 isomers, okay, with the branching going on. And then I drew out the cycloalkanes, because if I have an alkene, then I'm also I'm free to draw out cycloalkane. So here, start with the first ones, which is cyclopentane, and then I can go on to branching, okay, as much as possible. So there is that. I think this one is wrong over here, so we'll see. Okay. Constitutional isomers of oxygen. So as soon as you have an oxygen, the first thing, of course, you do is you figure out if you have an alkane or an alkene. Remember, oxygen doesn't count. Okay, so don't worry about the oxygen. So in this case, it is going to be all straight chain, going to be all alkanes also, which means single bonds. Okay, only single bonds. So here I have drawn all the alcohols. I moved the OH group one time, then I moved the carbons also. Okay, so I just went on, and then the last one that I drew out, this is for all the ethers, okay, in there. So I'll let you be, and I'll let you figure this out now that you kind of know the pattern. So in this case, for oxygens, I've given you again how you can decide, okay, what kind of constitutional isomers you can have. So something like C5H10O. In this case, you actually have an alkene, okay, which means you have a double bond. So once you have a double bond, okay, you can draw an alcohol with an alkene, cyclic alcohols. You can draw all these varieties of compounds, okay. I think I did this myself, and I did come up with 50, okay, or 40, excuse me. So you can draw a whole bunch, okay, of compounds using C5H10, C5H10O. So if I were to give you this kind of a compound in an exam or a homework and say, okay, draw me the isomers, I mean, it would be criminal for me to say draw them all, because, you know, you can see it's not possible. Okay, it's just possible, it just takes you too much time. So I will just have you focus on drawing all the aldehydes or all the ketones, something like that. Okay, so anyhow, try some of them out, okay, if you want to. Oh, guess what, I have done it for you. Okay, so go through all of these and you will see how fun it was for me to draw all of these out with the C5H10O. For this one is for acids. So again, you can draw acids if you have 2 oxygens, and you can also draw esters. Okay, it doesn't mean these are the only 2 things you can draw. You can probably draw 2 ethers or 2 alcohols with a double bond. Anything is possible, and you should probably try that out. Okay, but I just drew the acids and esters over here. And then amines. So in amines, we've talked about primary, secondary, and tertiary amines. So in the primary amine, NH2 is kind of hanging out there. So these are all the primary amines. And secondary amines, nitrogen is internal, it is inside, meaning that you have 2 carbons coming out. And in a tertiary, you have a nitrogen with 3 carbons coming out of it. Okay, there's no hydrogen attached to nitrogen anymore. So primary, I say 1 carbon attached to nitrogen, secondary 2 carbons attached to nitrogen, tertiary 3. All of these, they all have the same formula. They have the same molecular formula. look at how many amines we can draw with 5 carbons. Okay, so kind of go through this also just to see the variations for all these structures. So in any case, constitutional isomers is a fun game to play sometimes. Sometimes it's very annoying because like I think I got all of them and then I missed one. Or sometimes you miss a double bond, sometimes you miss an oxygen, sometimes you eat up a carbon. So all of these kind of things can happen. Okay, so know your functional groups well, because if you know your functional groups, then you have a whole board of drawing constitutional isomers. Make sure that you keep your carbon and hydrogen in control, otherwise, and I don't give you very big structures, okay, myself, because I know that can be overwhelming. So I don't give you very large structures or very large molecular formulas to work with. Okay, so at least have some peace with that, and then that's kind of it. Just practice, practice, practice.